Okay, so we're going to discuss this harmonic oscillator. Okay, so it's called harmonical, right? So later you're going to see why this one is harmonical. So before we, to discuss the solution of this, differential equations to find the eigenstates, eigenvalues using the mathematics. Okay, so we try to understand the physics as much as we can before we're doing too much calculation. Okay. So first of all, what's the Hamiltonian? Okay. So we know that if we have a harmonic oscillator, the potential in classical physics is given by 1/2 kx squared, right? So this k is just the coefficient for spring. Of course, you can have something like this one, right? So this is suppose this is the equilibrium, the position from the equilibrium point. Okay, right. So this one can be also written as 1/2 m omega squared times x squared. Okay, right. So the omega is just the angular frequency of the classical oscillator. So the Hamiltonian is the momentum squared over 2m plus 1/2 m omega squared x squared, right? Okay. So in classical physics, we have known that this harmonic oscillator satisfies a very simple equation. So the time derivative of the position is just given by the momentum divided by the mass. And the time dependence, the time derivative of the momentum is given by minus, the force. It's given the force, right? The force is minus gradient of the potential. So that is m omega squared x. Right. So if we want this roughly, states that the change of A. So A is the change of B, and B is the change of A, right? Of course, this is just a very loosely speaking, okay? Right. So you can say that if you change the position, that will cause the momentum, or if you change the momentum, that will cause the position, okay? So this one can be also similar to the LC circuits, right? For example, if you have capacitors, you can have something like this one. In this case, you have this capacitance, you have this inductance, okay? And then you have the charge. You also have the current. You know that the change of the charge is the current, and the change of the current, right, is given by the, will cause the potential, right? That will give you, let's say, minus the change of the current times L will give you QLC, right? Is that right? Something like this one. Okay, more or less, okay. So you can see that if you have LC circuits, you can also have something like a harmonic oscillator, right? So you don't have to have this one to be, mechanical. So you can actually have any variables that change by this kind of conjugate set of equations, and then you can say that this is something like a harmonic oscillator. Okay. And then for this one, you can also know that the LC circuit would also have some kind of oscillation, right? So the current will oscillate just like the position of a harmonic oscillator, okay? Or the charge will oscillate like the position of a harmonic oscillator, okay? So this is the classical physics that we have for the harmonic oscillator, right? And this one actually, as you can see for these two examples, it actually can be applied to many different problems, okay? Especially the harmonic oscillator. The harmonic oscillator actually is approximation, a very good approximation actually, of so-called low energy or low temperature physics, okay, of many systems, okay. So in many physical systems, okay. And for example, you can consider the vibrations of molecules. For example, you can have a carbon. You have carbon monoxide, right? And then you know that and these two actually can be something like it's almost like a spring connected by these two atoms, so they can vibrate. Okay, and this vibration actually causes the absorption of the of the EM fields. Okay, for example, if you have carbon dioxide, let's consider carbon dioxide. Right. So the absorption of carbon dioxide actually causes the absorption of those infrared light, and this one is the physical mechanism of the greenhouse effect. Okay. Right. So you can also have vibration of atoms in the solids. Okay. So they're also like springs connected. So you can have atoms, right? They can form a kind of lattice. Right. So you can have a lattice, okay? So these are actually the forums. Okay. And it was first studied by Albert Einstein, right? Okay. And that was useful for studying the specific heat of those vibrations of the solids due to these vibrations or due to these forums, okay? Right. You can also have, for example, so-called spin waves. So we have not known spin yet, okay? In magnetic materials. Okay, that's called a mechanism, okay? You can also have, of course, EM field. That's a photon. Okay. So there are many kind of physical systems that can be understood by the physics of harmonic oscillator. Okay, so it's very important to understand those beautiful physics of the harmonic oscillator. Okay, and also you can see that if you have a potential like this one, suppose in general you have a potential, right? So this one, of course, is not a harmonic oscillator. Okay, but if you interested in the low energy physics. Okay, so if you look at energy levels, so this is the energy level. So the wave function we are mostly within this quantum well, this part. But of course, if you have so the wave function will more or less like this one. Okay, and then you have the first excited state, and then you have the okay. But then for the high energy, for this one, you also have some state like this one. The wave function will more or less like this. Okay. But then for the high energy states, and then you can have the mixing of the two quantum wells. So that means the wave functions will be in both sides. You can have something like this one. Okay. But and then in the very high levels, you can also have wave function like states like this one. Okay. Okay, you can have many states. But suppose you are interested in this kind of low energy physics. That means if the temperature is very low, okay. And then the system will be stay at almost the ground state. And there's a little bit of excitation in the higher states, but more or less occupy this one. And then you can approximately take this potential to be as if it's a harmonic oscillator. So this V x prime approximately can be written as 1/2 m omega squared x squared. Okay. The reason behind this one is that if you have a potential, okay, if you look at the low energy physics, you always look at the motion, okay. So you always look at the motion close to the equilibrium point, right? So that means you can do the tidal expansion at this point. So you can do the tidal expansion. So Vx can be written as this V minimal. So this one is so V0, right? And then plus the first order derivative V prime at this position, and do the tidal expansion, right? You can also have the second order term 1/2 factorial at this point, and then have the square term. Of course, you can have higher order terms. Okay. So at the equilibrium point, so we must have V prime x0 equal to 0, right? So that means we can just have this term to be crossed. Of course, you can take it doesn't hurt. You can just take V0 equal to 0, right? Because in physics, you can always change the potential by constant without changing physics. Okay, right? So you can only change all the energies by a constant. And also, it's up to you to choose the coordinates. Which one is 0? So you can also take this one equal to 0. Okay, and then consider this x minus x. This one is small. So you only need to keep it the leading order terms. So the leading order is just Vx equals to 1/2 m omega squared. Just the second order term, right? 1/2 V prime prime x0, that equals 0, right? And x squared. Okay. So this one gives us the the potential, right, at this this point, okay, approximated by the potential of a harmonic oscillator, right? So you can see that this harmonic oscillator can be a good approximation if you are interested in the low energy physics at the thermal equilibrium, okay? So that means if you are interested in the low temperature, okay, at equilibrium, okay, so V approximate to 1/2 m omega squared x squared, okay, right? So this is the reason why this harmonic oscillator is actually a very useful model to describe the physics. Okay. Okay. And as an example, we can also consider this EM field. Right. So we know that we have E and the B. We have this one. Of course, there's a Maxwell equation, right? So the Maxwell equation tells us that this is the change of the change of the electric field is a proportion to the B field, right? And the change of the B field is proportional to minus the E field, right? So you can really change compare this one to the momentum and the position. This pair, right? And actually, if you look at the energy Hamiltonian, okay. So this is more or less just 1/2 epsilon 0 square E squared and plus 1/2 1/mu 0 and B squared, right? So this can also be compared to the harmonic oscillator, okay? So you can see that in this case, the EM field, okay, if quantized, will be just the harmonic oscillators. Okay, so this actually is an important basis for studying the quantum field theory. Okay, especially the quantum electrodynamics, the quantum electrodynamics. Okay, right. So this is another example that we have a very nice analog between a physical model, a physical system, and the harmonic oscillator model. Okay. And this harmonic oscillator is also very interesting in that if you have the constant force, okay, actually the physics is more or less unchanged. Okay, so this problem can be solved without much effort. As long as you know the solutions of a harmonic oscillator, you can actually immediately find the eigenstates, eigenenergies of harmonic oscillator under force. Okay, I know that the Vx originally is just 1/2 m omega squared x squared, right? And now you have a force F. Okay, so this force is F. So that will cause you another potential, right? Suppose this is the original potential. That's 1/2 m omega squared x squared. Okay. Right. And now you have this new potential, but this new potential actually is the same as harmonic oscillator because this linear term can be always absorbed into this square terms. Okay. Right, so we can write down this as 1/2 m omega squared x minus x0 squared. What is this x minus x0? So this x0 actually is a new balance point, okay? But to make this perfect square, you need to have one more term, okay? So minus 1/2 m omega squared x0 squared. And this x0 should be the balance point. That means if we apply a force on a spring, for example, you're going to stretch the spring to one direction. Okay. Right. So suppose you have a spring. Okay. And then you apply the force. And this will actually move this one to a new position. Okay. And at this new position, the force should equal to the dragging force by this spring, right? So that is m omega squared x0, right? Okay. So that means x0 must be f over m omega squared, okay? Right. So that means as long as the force, and this one will be, the new balance point will be here, right? Okay. And then the potential, the energy, the minimum energy will reduce a little bit. Okay. But the shape of this one actually is unchanged. Right. So this one is x0, and this one is minus 1 over 2 m omega squared x0 squared. Okay. Right. So that's the reduction of this energy. And then you know that if you have the energy states of this one obtained, okay, and then automatically you just have the same energy, you know, with the same spaces, but all of them will be shifted by a constant, and also the wave functions will not be changed except for displacement. So that means you have the percent mx will just change to be percent mx minus x0, and the original energy, eigenenergy of the system will be just changed to be em minus this 1 over 2 m omega squared x0 squared. Okay, and as we have seen before, all those kind of measurable quantities are just related to those energy difference. Okay, they are not affected by a global change of the phase factors or a global change of the energy. So that means the physics is more or less the same, right? So if I have a constant force applied to the harmonic oscillator, okay. So this is one thing that I want to mention about this harmonic oscillator before we're doing any calculation, right? Okay. All right, so now let's move a little bit more to the mathematics. Okay, so we want to look at this Schrödinger equation. We need to, our task is to find out the solutions of this Schrödinger equation. Right, so that is minus h bar squared over 2m d squared over dx squared. This is a term from the kinetic energy, and then you have a potential energy. Okay. Right. So this is something that we want to find. So what's the energy? What's the possible, allowed, acceptable energies for this system? And what are the eigenfunctions? Right. So these are the task we needed to to do in this lecture. Okay. But before we proceed, you can see that this equation looks quite annoying because there are many coefficients. Okay, and to simplify the problem, okay, we want to make this equation, to be more or less dimensionless. So that's one thing. Another thing is that we say that low energy physics, for example, but low or high, these are relative to what? Right. In physics, when we say something is big, something is small, something is low, something is high, we are always talking about these things in a relative sense. Okay. You know, in comparison to some typical energy scales. So in this harmonic oscillator, we actually have typical scales of length, momentum, energy. Okay. But the question is that we have m, omega are the only two parameters. Okay, of the system. So if you have only the two systems, we know that if you look at the dimension, okay, and this m, of course, has dimension just mass, right? Okay, and this angular frequency has dimension just 1/4 time, right? So that means we have no way actually to form typical length scales and momentum or energy using these two parameters. But remember, in the quantum mechanics, we have h bar. So this is a providence of the nature to us. So we have a natural constant in quantum mechanics. So that means we have another parameter which gives us dimension, that is energy times the time, right? Okay, and you know that once you have this three parameters, you can actually form natural quantities defined by these three parameters: Planck constant, mass, and omega. You know, to form these typical scales of length, typical scales of momentum, and typical scales of energy. How do we do this? Let's do this one by one. Okay. Right. Let's look at the potential energy first, okay? This potential energy equals to 1/2 m omega squared x squared, right? And this one, of course, has the dimension of energy. So we want to have energy. So we write down this as h bar omega over 2. And this one, of course, has the dimension of energy. And then what's left will be m omega over h bar, right? So this is a quantity. And then times x squared. Okay. So this one is energy. And this one is length squared. So that means this one must be length to -2, right? So that means we can define a typical length, which is just square root of h bar over m omega. Okay. So this is the length scale. Right. And then similarly, automatically we have already determined the energy scale, right? So this is the okay. That's automatically at this energy scale. And you can look at the momentum then, okay? For the momentum, we look at this kinetic energy. So kinetic equals to P squared over 2m. Again, we write this one as h bar omega. This is the energy scale over 2. Okay? And then to make up this one, you must have m times h bar omega times p squared, right? So this one, of course, is the energy. Okay? And this one is the momentum squared. Okay? So of course, and this one will just leads to a typical momentum scale that equals to square root of m h bar omega. This one, of course, can be written as m times the energy scale equals to h bar divided by the length scale. Okay, so that gives us the momentum scale. Okay, so that means in this Schrodinger equation, we actually have two parameters, mass and frequency. But in quantum mechanics, we have one more. Okay, we have mass, we have omega, but we also have this h bar. So we have these three parameters, so we can form typical energy scales, typical length scales, and typical momentum scales. So that one means when we study the physics of the harmonic oscillator, once we want to compare, say, if I have a large amplitude oscillation, for example, if I have a large energy, if I have small energy, if I have a small oscillation, all of this one, or if I have a large fluctuation, we have a big fluctuation, we have a small fluctuation, we should always compare those quantities to this length scale, to this energy scale, to this momentum scale, depending on what kind of quantities you are looking at. And this means probably it's also interesting if we just write this time-independent Schrodinger equation into, this unit of system. So we use this length scale as a unit of the length, use this momentum scale as a unit of the momentum, okay, and so on for the energy, okay. And then we can have a transformation like this one. So this X operator is the original operator, but divided by LC. So this is the position operator in units of LC. Okay, and this momentum, of course, can be also written as this. So this is the momentum operator in units of PC, right? The momentum scale. And the energy, we can also define this energy that equals to the original energy divided by h bar omega. So that is the energy in units of EC, right? So from this one, we obtain a dimensionless Schrodinger equation, okay? That is 1/2 p squared plus x squared cosine m equals to okay? So this one is right. This is it's beautiful, symmetric. It's a circle in phase space, right? So you can see that if you have something in the phase space x and p, you know that the motion will be just a circle. Okay? Because the Hamiltonian has this position and momentum to be just on an equal foot. Okay, so that's actually extremely a beautiful feature of this harmonic oscillator. Okay, so you should stare at this equation and be awed of this kind of a beautiful thing, right? So you can see that there is a kind of very essential fundamental symmetry in this harmonic oscillator. Not only is that the potential is symmetrical, but also there is a symmetry between the momentum and the position. Okay, right. So that's one of the reasons that we want to spend so much time on this harmonic oscillator. Okay. All right. And now we want to talk a little bit more about this dimensionless position and momentum. Okay. So we know that for the original position and momentum, we have this commutator. That's very important, all right? This actually is the most important thing in quantum mechanics. You know, especially for those matrix form of quantum mechanics. And now we can look at this x and the p commutator. So now I can prove this one actually just equals to I, right? Because you can see that in this new unit system, h bar is just one, right? H bar is just a unit because the energy is h bar omega, right? So to prove this actually it's very simple. So because x p just use the definition. Just this one. So that means this one equals to 1 over LC times PC and x and p, right? That's the physical position, the physical momentum, okay? And that one, we have that one equal to IH bar, right? Divided by LC and PC. But remember, PC equals to H bar divided by LC, okay? So that equals to I, right? Okay, so this is one a beautiful thing about this kind of dimensionless position and momentum, okay? Right. And also, if you write this one as an operator like this, okay, and then you should similarly you should have this one. Okay, so that means this dimension momentum can just be written as a differential operator with respect to this dimensional this position, right? So you can check this commutators using this definition, okay? All right. Right. So what's left is just we need to find the what's left is that we need to find the solution of this one, right? Okay. So this is the thing that we need to find. Okay. So what's this? And what's this? Okay. And if we find this one, the energy in the physical you know system will be just h bar omega times epsilon m, right? And then the physical wave function, okay, will be just be simply times 1 over square root of LC. So this one is for to make the dimension to be correct, and also to keep the normalization. So this one is the x-axis. You can check. Without this 1 over square root of LC, you will not be able to make this wave function to be normalized. If the original is normalized, okay, and also you will not have the correct dimension for the wave function, okay. Right. So then next, so we're going to discuss this dimensionless Schrodinger equation. So we're going to use this dimensionless Schrodinger equation and to find the solution of this one. And once you have found a solution for the dimensionless equation, you can easily just obtain the energies, okay, in physical units and the energies and the wave functions in the physical coordinates. Okay. All right. So let's take a break at this point, and let me know if you have questions. Okay. So we have seen that we need to find a solution of this Schrodinger equation, right? That has a very beautiful form, okay? Okay. So the solution of this one actually have some features that we would like to mention before we give the specific form, okay? The first of all, we see that this potential goes to infinite if x goes to plus or minus infinite, right? So that means, you know, this percent mx should goes to 0, okay, for all equation m, right? So this means all states are bounded states. Okay, so there's no continuum or scattering states. Okay, so this is one thing of this harmonic oscillator. Okay, right. Another thing that so if this one goes to 0 at the infinite, so we can probably like write that this one goes to something like this. Okay. Right. So this one should decays to 0, right? But remember, if we have a potential like this one, okay, in this case, if v goes to v0, we know that this fx will goes to a constant times x, right? So that means it has exponential decay, okay? But now this v actually is v of this harmonic oscillator is something like this one, okay? So this one goes to infinite. So that means we must have fx should be much greater than x, okay? For large x, right? Okay. So this is one thing that we should keep in mind. For example, you can have fx equals to some constant times this x to the power beta, with this beta greater than 1, right? So if we just equal to 1, you should have something like an exponential decay. In that case, you should have a potential that's kind of a constant at the infinite, okay? Which of course is not the case for harmonic oscillator. So for harmonic oscillator, if you write down this as an exponential function of some function, and that function should goes faster than the linear function, okay? Right. So this is another feature that we should have for this, okay. And also, we have this potential to be symmetric, right? So we have, that means the parity is a good quantum number. Okay, or each states should have definite parity. Okay, so that means percent mx should equals to -1 to the power m percent minus x for m equal to 0, 1, 2, and so on and so forth. Right. So now we use the first state is 0 state. The second is the first state. Okay, just for convention. Okay, so by convention, m starts with 0. Okay. Right. So you have an even function. Okay. All the function, even function, all the function, right? Alternatively, okay. So that means if we have a potential like this one, okay. So and then the lower state, the 0 state, will be something like this, and then the first excited state will be something like this one. Sorry, this is bad drawing. Something like this one. And then the third state will be something like this. It's an even function. Okay. Okay, so this is the percent 0, percent 1, percent 2, right? So on and so forth. Okay. We don't need to know the specific form of this this point. Okay, but we know that it must be odd function, even function, alternatively. Okay. And also, because of this one, because they are even function and odd function, so you know that and then percent m x times percent x, and this must be even function, right? Okay, so this means the expansion value of the position momentum must be 0. Okay, of course the bounded states of momentum should also be 0, right? So if I have the momentum of a bounded state, it must also be 0. But in this case, in this specific case, we can also use the symmetry, okay, to prove that the momentum has 0 expansion value. Okay, right. So this is another feature of this states. Okay. And now I want to say that there is an even more beautiful future for this state. Remember, in the Hamiltonian, right? So this one has this kind of exchange. If you do the exchange of x and p, okay, you actually will not change the Hamiltonian. So this means if you do the wave function, suppose you have wave function in the momentum space, in the coordinate space, position space. If you also write down this, do a Fourier transform into this one, so with percent m p just given by e to minus I p x percent m x dx over square root of 2 pi. If you do a Fourier transform, this one should have the same form as percent mx. So this is a tremendously beautiful property of the eigenfunctions of the harmonic oscillator. So what kind of functions have this property? Do you remember anyone? So anyone can think of a function that has a Fourier transform of the same form as its real space function. Any of you have encountered this kind of function? Yes, wonderful. Gaussian, right? Gaussian function. So this actually gives us a huge hint of the eigenstates. For example, e to minus x squared over 2. So this will be a very nice point for us to start with. Okay. So if you have this function, and then you do the Fourier transform, that will actually minus p squared over 2. Okay. So this is a very beautiful function. Okay. So Gaussian function is a beautiful function, and the eigenstates of harmonic oscillators, they should be all kinds of these beautiful functions. Okay. So you can see that there will be not only one, there will be infinite number of such kind of wave functions that has the Fourier transform to be just itself. Okay. So this is something extremely beautiful. Okay. So I want you keep this in mind. Okay. And also, for the same reason, because of this symmetry, right? If we change x and p, they should be the same, right? So you must have you must have this one should equals to this one, right? Of course, because you have percent x. Right. So these two are the same, right? So that means if we calculate the average of a physical quantity, they must be the same, right? And we also have this one equals 0 is known, right? So that means we must have delta x, the variance of x, and the variance of the momentum. This must be the same, right? Okay. And look at the energy. The energy is just 1 over 2 x squared plus 1 over 2 p squared. It's just momentum energy, the kinetic energies, and the potential energy, right? And this one now should be just 1 over 2 delta x squared plus delta p squared. So this is a very beautiful formula. You know that the energy of a state, the average of the energy of a state is just given by the fluctuation of the momentum and the position. Okay. Of course, by very simple mathematics, you know that this one must be of this one, right? And then you know that delta x and delta p should be greater than h bar over 2, right? So because of this one, so we must have this one should be greater or equal to 1 over 2, right? So what does this mean? So that means the energy should be greater or equal to h bar omega over 2. Okay. So this one, the energy has kind of a lower bound. Okay. So that means the minimal energy of a quantum harmonic oscillator is non-zero. And the reason is that because of the fluctuations of x and p. So this is a very important physical observation. Okay, the fluctuations of physical quantities actually makes this energy to be non-zero. Okay, so actually you can consider, for example, if you want to, you can consider. Let's consider, suppose you have a state. Let's try to minimize the energy. Okay, you know. Okay, so this is the potential, right? And now you can have This is energy. So if you want to minimize this energy, for example, you can minimize the potential energy. Of course, you want to have x goes to 0, right? So that means you should have a wave function goes like this one. Okay. Okay, in this case, v goes to 0. But then, if we do the Fourier transform of this one, this will be something like a very broad, right? Because a narrow function in the real space will give you a broad function in the momentum space. So that means the kinetic energy goes to infinite. Okay, so this is not good. Okay. And this one is happy, but this one is unhappy, okay? Of course, you say that, how about if I try to minimize kinetic energy, okay? So that means if I minimize kinetic energy and make this P goes to 0, okay? That means the kinetic energy goes to 0. But then, in the real space, so this will be very broad, right? So this percent x will be something broad. And then the potential energy will go to infinite. Because the wave function penetrated into the barrier will increase this kinetic energy. So potential energy, sorry. So that means the two must be, you must have a trade-off, right? And you know that if you look at Hamiltonian, the Hamiltonian is symmetrical in position and momentum. So this means the trade-off must be equal distribution, right? You must have equal partition of this energy into the kinetic energy and the potential energy, okay? So that means the state, the eigenstate, the minimum, the quantum state. Okay, so the quantum state is kind of a trade-off between k and v, right? Actually, you should have x squared equals to p squared. Okay, so that means you can have the same kinetic energy and same potential energy to minimize this eigenenergy, okay? But you cannot make this one to be 0, okay? Because the fluctuation will make this one to be always positive. So this is fundamentally different from what we have for classical, okay, mechanics, right? For the classical mechanics, the harmonic energy, this E goes to 0 at x equals to 0, right? So you just place the particle at the potential. So this is so if I have classical mechanics. Okay, we just have a particle right here. Okay, so this is classical mechanics. Okay, so x equals to 0 and p equals to 0. So this one, let us energy equals to 0, right? Right. So in quantum mechanics, so you must have this energy is always positive. Okay, so this is 0 point energy. So even if the system is at a quantum center, you still have energy. So that's a very important thing about this. This kind of thing. Okay, right. So this is the 7th point. Okay, so these are the general properties. You know, even without doing too much calculation, we can derive just by staring at the Hamiltonian, okay? Just by looking at the Hamiltonian and do some observation, okay? So this is always a way to do physics. Before you hurry up to do some complicated calculations, always try to cool down and take a break and look at the equations and think about this problem, okay? And look at the problem for a while and see how much you can squeeze out of the equation just by by meditation. Okay. Okay. All right. So we're going to do this meditation furthermore and see. We try to squeeze as much as we can, right? Okay. So let's continue this process. Let's guess the eigenstates. Right. Remember, we know that we should have a percent x to the Fourier transform. So you just got a percent MT at T, right? They are of the same form, okay? So this just equals to percent MT. And we know that the Gaussian function have this property, right? Have this property. Also, this one, let's call it a Gaussian function, okay? And this Gaussian function is symmetric. Okay, so the parity equals to +1. Okay, and this one is not 0, does not equal to 0 at any point. So the number of nodes equal to 0. Okay, so that means so very much possible that this Gaussian function equals to the quantity set, right? Because the quantity set should have even parity, should have a number of nodes to be 0, and it should have its Fourier transform to be self. Okay, so this one is okay, this one is okay, this one is okay. Okay, so do we have this one? Okay, so let's just guess. We put this back into the equation and check. Okay, so we check this equation. So this one equation should be 1/2 d over dx squared minus and plus x squared. We check this one. Okay. This calculation is very simple, right? So you can do the differential of this one by once, okay? So this will be just be minus x e to x squared over 2, right? And do this one twice. Okay, you do this one twice. So that means you do the differential once more. So of course this one can act on this or can act on this. Okay, so that gives you two terms. The first one will be minus e to minus x squared over 2, right? And the second term will be just plus x squared e to minus x squared over 2. And then you put this back in that one. So you can see that the left hand side just 1/2. Okay, there's a minus sign right here, remember? And cancel this minus sign. So this is plus e to minus x squared over 2. And then this will be minus, so I get a minus x squared e to minus x squared over 2. And then you have this term, right? So that's a plus x squared e to minus x squared over 2. So very nicely, this term cancels this term, right? Okay. So this one just equals to 1/2 e to minus x squared over 2. That's beautiful, because e to 0 just equals to 1/2. Or the energy 0, the quantity energy just h bar omega over 2. Remember, the expansion value of this energy must be always greater or equal to this one, right? So that means this must be the quantum state. You cannot have a state with energy lower than this one. Okay? So we have checked this one. It's correct. Okay? I'm very happy. With very little efforts, you know, we have squeezed the quantum state out of the equation, right? We don't need to solve the differential equation. Okay? We just guess and then we find the equation. Okay, and we continue this process. So how about the 1x? Well, we know that it should be x, sorry, it should be an odd function, right? So the parity equal to -1. And also, this one equal to 0 at 1x0, right? And if you have an odd function, if you have 1, 0, so which one should be a 0? Can you tell me what's the solution? So what's the solution? So you must have x0 equal to 0, right? So that means percent 1x okay. So it should be a wave function like this. Okay. So we can just guess, right? The guess. So if I have one function that goes this one, and also this one should decay faster than that one, so we should have this one. Let's say just write this one as e to alpha x squared, and this one we simply write down this as x times this one. Okay. Right. Then we check. We put this back into the equation. Okay, we put this into the equation, and we find that this percent 1 actually is proportional to x e to minus x squared over 2. Okay, you can continue this process. Actually, you know that what's the second function? What's the next one? So next one, we should have percent 2x should be even 2 nodes. Okay, you know that if you have even function with 2 nodes, most likely, so it should, we know that if you have a polynomial of second order, you should have 2 solutions, right? So we guess it should be a plus b x squared, and this one is you must have something like this one because the solution must be symmetrical, right? Okay, and this one should be minus alpha x. And check. The result is percent 2x proportional to. So you can see that I cannot remember the coefficients. So you don't need to remember this coefficients either, okay? But you know that you just by insert this one into the equation, okay? And similarly, you find this the third state will be x times, so you have one solution at x equal to 0. So you must write the x times something, right? Again, like this one. And check. The result is okay. So you can continue this process, and the bigger guess is like this one. Okay. So this will be certain polynomial, right? Okay. And also look at the energy. Let's check the energy. The energy for this one so the energy for this one actually is 3/2 times h bar omega. And easily you can also check this energy, E2 equals to 5/2 times h bar omega. and E3 is 7/2 h bar omega. Okay, so you can guess this one. We guess the energy will be just m plus 1/2 times h bar omega, right? So this is the, of course, is of guess. Okay, and then again, we can check this one. Okay, but now we have obtained so much about this, eigenfunctions, eigenstates. Okay, without really solving the differential equation, right? But of course, you want to know how can we really solve this problem? Okay, if we really want to learn how to solve these equations by a systematic method, okay, because we may not be always so lucky that we have such a beautiful problem, so that we can squeeze so much out of the equation without doing any real calculation, right? Okay, and so let me take a short break and see if you have questions. Okay, and then I will continue to introduce a systematic method to solve the Schrödinger equation for harmonic oscillator. Okay, and that method actually can be generalized to many physical problems. Okay, but let me pause for 1 minute to see if you have questions. Okay. For example, I can have a question for you. Why not try e to minus, say, for example, alpha x to the fourth power, or e to minus alpha to x cubic, etc. Right. So why did we try this one? Okay. So the reason is that actually, the reason is remember percent m x. If we do the Fourier transform, you should get a percent n tiered p. That one actually equals to, or at least is proportional to percent m p, right? So you just need to, so they have the same form, okay? So the example of this one is, of course, x squared over 2 will give you minus p squared over 2, right? So this is something that we have known, okay? But how about e to minus x to the power m over 2? How about this one? Okay. So in this case, we know that you have a Gaussian wave packet, okay? So this is like this one. So this is percent x or percent p, right? So that's Gaussian, okay? But what if it's not a Gaussian? So if it's not a Gaussian, for example, if n is greater than 2, okay? So you can have something like this one. So this is, for example, n equal to 3. And if we have a bigger one, even bigger one, so you're going to have this one to be so this is the case n equal to 4. Or if we want to have even bigger index, so this is n equal to, for example, 100. Okay, so you can see that if n increase, okay, and this function actually will become more and more like a square function. And you know that if we do the Fourier transform, okay, if we do the Fourier transform, we know that the sharper h leads to long tails. So that means original, this is suppose you have a Gaussian function. So this is Gaussian. Okay. And then you have something with very long tail. That's a non-Gaussian. So that means you can say that this one cannot be correct, right? So that means you shouldn't have n greater than 2, because n equal to 2 is just the right index such that the tails of the transformation, the Fourier transform, is also Gaussian, the same as real function. So if you make this n to be larger, that means the change of this function will be sharper. So you can have longer tail in the momentum space. So that means you have an index less than 2. Okay. So this means to make this two to be exactly the same, you must have this one to be a Gaussian function. And then of course you can have some kind of polynomial, because the polynomial will not change this sharpness. Okay. So that's one question I would like to ask on behalf of you. Let's say, any other questions? How can we obtain, yes, great. How can we obtain the energy E1 and E2? Let me check one for you, okay? This is a good question. By guessing, right? Okay. So let me check this one for you, the answer, okay? Let's look at the example. We guess this function should be equals to x e to minus x squared times alpha, right? So that's our guess. Okay, we insert this one into the Schrodinger equation, okay? So then we're going to have minus d over dx squared plus x squared, and then x e to minus alpha x squared, right? We check this one. So this one should equals to, of course, we have one term, x squared, right, times x e to alpha x squared, right? So this is comes from this term, okay? And then you do a differential twice. Let's do a differential twice. Let's do this one, d over dx, x e to minus alpha x squared. So this will give us two terms. The first one will be just simply, you act on this one, right? And then the second one will be minus 2 alpha x squared e to minus alpha x squared. Sorry, this is alpha. Okay, now you do this one twice. So you have to do this one again, right? So that will give us let's say the first one will be minus 2 alpha x e to minus alpha x squared, right? So do this one. And then another one you got a minus 4 alpha x, right? So you do the division on this one. And then you do the division on this one again. So that will give you another minus 2. So that could be plus 4 alpha squared x cubic, right? E to minus alpha x squared, okay? So and there's a minus sign. So the pro minus sign right here. So this one will be changed out to be plus and plus, and this one will be minus, right? Okay. So you can see that so basically you need to plus 2 alpha x e to minus alpha x squared, and plus 4 alpha x e to minus alpha x squared, minus 4 alpha squared x cubic e to minus alpha x squared, right? So you can see that these two terms are of the same form like this one, right? So that means we can keep this two terms if we want this one to be eigenfunction. But you have an actual term. This is x cubic. This one's also x cubic. But if you take So if you take alpha equals to 1 over 2, okay, and then these two terms will be cancelled, right? Okay, you find that okay, that will equals to alpha equals to 1 over 2. So this 2 alpha will be just 1. 4 alpha will be just 2, right? So this will equals to say 1 over 2. That will be 6 alpha. That's 1 over 2, sorry. So there's 1 over 2. So there's 1 over 2. So there's 1 over 2, right? So this means epsilon 1 equals to 3 over 2, right? So E1 just equals to epsilon 1 times h bar omega, that equals to 3 over 2 h bar omega. So basically, you just insert the function, this gas function, into the Schrodinger equation, and then you can find out the solution. Okay, so that's the method. Okay. Okay. Great. All right. So now let's try to a systematic method to solve this equation. Okay. So we use a series to do the solution. Okay. Right. We know that by the argument, we know that this percent nx should be, proportional to a kind of function. We don't know what it is, but it should be a function e to minus x squared over 2, right? Okay. And we should have 1 over 2 minus d squared over dx squared plus x squared, okay, of this one. That equals to epsilon m okay. Right, so we just need to determine this part. Okay. And then we can act this one on this. So we know that you can have the left hand side. Okay. We have let's do this way. Okay. Let's look at the differential of this one. This one is the difficult part, right? Okay. So this one, of course, you can have two terms. One is the derivative of this one. Okay. I have another term. That will be 2. There's no 2. Okay. That's x. Right. Then you do this one twice. Okay. Of course, you can get a h prime prime mx e to minus x squared over 2, right? But you can also do this one on the second part. So that will give you minus x hm prime e to minus x squared over 2, right? And then you can do the same thing for the next term. So that will give you, first of all, okay, and then you have minus x hm prime e to minus x squared over 2, right? And then finally you have a plus x squared hm x e to minus x squared over 2. Okay, all of them have this factor, right? Okay, so you can take this one out. So that gives you x prime prime m minus 2x hm, the first order derivative. And then you have plus x squared hm, and then minus hm, e to minus x squared over 2, right? Okay. Of course, you can, and then you insert this one into this. Okay. So you obtain the equation that's 1 over 2. Okay. There's a minus sign, right? So it's minus hm prime prime minus 2x hm prime plus x squared. Sorry, there's a sign change. But this is a plus. There's a minus x squared hm plus hm, right? And you have this term, so minus x squared hm e to minus x squared over 2 equals to epsilon m hm and e to minus x squared over 2, right? And of course, this term and this term could be cancel each other. And this term and this, so this is plus. These two terms cancel each other, right? Okay. So combine all of this one, you got a, equation for this one only. So that will be hm second order derivative minus 2x hm first order derivative. And then you have plus 2 epsilon m. Let's say it's minus 1 plus 1. Should be minus 1, right? hm. And this one should be 0. So that's the equation for us. Okay. So we just need to solve this equation. Okay. And we know that we have a guess for this hm should be some kind of a polynomial. Okay. So that means we are motivated to expand this by into series. Okay. Okay. So this one can be summarized into the equation like this. Okay. Right. So that's something that we need to find out. Okay. So minus d squared over dx squared plus 2x d over dx plus 1 minus 2 epsilon m hm x should equal to 0. And then we do this one. We'll write down this one as a series. Okay. Right. So that's something that we want to find out. Okay. We put this one into this one and compare them order by order. Okay. So you can see that if we do the first term, okay. So that will give us 0 plus 0 plus 2 times 1 times a2, right? And then plus 3 times 2, a3 x. Right. So this is the terms that we have, right? And you look at the second term. So that's 2x d over dx. Okay. So the first one will be again 0, right? And the second term will be 2 times a1 times x, right? Okay. And then plus 2 times 2 times a2 times x squared. Okay, so on and so forth. Okay. Of course, you have also this term. Right. So, and then you need to make sure to make this one to be 0. You must have all the coefficients, collected to be 0 for each order of this x, right? Okay. So you have so the resultant, expansion. Okay. So you must have. If you look at this one, will give you minus for the nth order. Okay. So m plus 2, m minus 1, a m plus 2, right? So this is from the second order derivative. And then you should have 2 times m, okay, times am, right? So this also gives the nth order. And of course, you have 1 minus 2 division of m times am. And all of this one should be 0, right? Okay. And this one, of course, give you a solution. Not a solution, give you iteration equation, okay? So you can see that once you know am, you can know am plus 2. So am plus 2 will just equals to 2m plus 1 minus 2 epsilon m divided by m plus 2, m minus 1, m plus 1, sorry, am. So that means you needed to have a0 and a1 no. Okay. You should have a3, a4, and a2, sorry, a3, a4. All of them would be no, right? Okay. So there will be two coefficients to be determined. But remember, we always have this differential equation that goes to 0, right, at the infinite. Okay. So that will give us some constraints on this one. Right. So we will determine this, sorry. We will determine these coefficients, okay, by those boundary conditions. Right. So let's consider, so if we have an even function, remember the states have a definite parity. Okay. So that means HMX should equal to minus 1 to the power m times HM minus x, right? So that means should be even or odd functions. Okay. In this case, a0, a1 will equal to 0. In this case, you have a0 equal to 0, right? So that means we just have one coefficient to be undetermined, right? But remember, we always have a normalization factor that can be used. So that means we can actually fix the states. Okay. So this is one thing. Let's consider, for example, even states. Okay. So we can have a0, and then you can have am plus 2 just equals to 2m plus 1 minus 2 epsilon m divided by m plus 2, m plus 1, and am, right? And now if n goes to infinite, if n is large, you find that this am plus 2 approximately will just equals to m plus 2, 1 of am, right? So this is for large m. And these are the terms that's relevant for large x, right? That means x goes to the infinite. And with this one, and you can see that by doing the summation, so you can see that this HMX will be approximately just equal to, because they're only even number terms, right? Summation of k equal to 0 to infinite. And then this will be 2 to the power k, and this will be 2 to the, let's see, x to the power 2k, right? And this will be, let's look at this. And 2 to the power k, and k to the power factor, right? Okay, yes. And this one will be something like a x squared, right? And then in this case, you actually got a solution. And this percent x will goes to HMX e to minus x squared over 2. That will be in the order of this one. That goes to infinite. This is obviously unphysical, right? So you should have a wave function that diverge when x goes to infinite. This is impossible, okay? So something's wrong, okay? So let's check back when this one is wrong, okay? Let's go back. So since all of this one is correct, this one is correct, right? All of this one looks very similar, very normal. But then look at this one. So this one, of course, you can go from A0 and then A2 and then A3. And this one, of course, will continue. Unless at a certain point, unless at a certain m, you have 2m plus 1 equals to e epsilon m times 2, or e epsilon m equals to m plus 1 over 2. Remember the solutions that you have guessed, right? So that means the well-behaving requirement. This actually is the boundary condition, right? Of this percent mx goes to 0 at plus minus infinite. Will lead to that this energy must to be certain integer number plus 2. That is the quantization of energy. So Em equals to m plus 1 over 2 h omega are only allowed values. Right, so this is actually a very general feature of bounded states, because you must have these wave functions to be well-behaving. So then this eigenenergies must take in discrete value, okay? Okay, so now we have at least immediately obtain this eigenenergies. Okay, so this is h bar omega over 2. And then the next one is 3 over 2 h bar omega. And then another one is 5 over 2 h bar omega. And then 7 over 2. Okay. So all of this one are equally spaced. Okay, it's like a ladder. Okay, right, and all of this one comes from this condition. But remember, if we don't have this one, the wave function will diverge. Okay, right. So that's why we have discrete energy for the bound states. Okay, and then of course, so now you, for each of this one, you can actually obtain the wave functions. Okay, so the wave function is going to be determined by. So you have epsilon m equals to m plus 1/2, right? Okay, and you also have for the psi m x equals to a0x for even states. And the last term will be am x to the power m. This for m equals to 2k. Okay. And then for the order states, that equals to a1x plus a3x cubic, and plus again am x to the power m for m equals to 2k plus 1. Okay. Right. And with this iteration, I plus 2 equals to 2i plus 1 minus epsilon m divided by I plus 2 times I plus 1. Okay, this is the iteration. Okay, should be the polynomials only. Okay. Okay, and this HMX has the name. It's called a Hermite polynomials. Okay. Right. Once you have obtained this one, so you actually solve all the equations. Okay. So let me give you a few examples of these polynomials. Okay. Right, so the first one, that of course has only one term. The second one is 2x, and x2 is 4x squared minus 2x, and h3 that equals to. Okay, so you can continue this one. Okay, you can check a mathematical book, or you can just look at the lecture notes. Okay, so you can also verify an exercise. Okay, they indeed satisfy this kind of equations. Okay, so basically, so we have solved the equation, right? Found all the eigenstates and eigenvalues by this series method. Okay, all right. So that's a very systematic method. Okay, so you can actually for any kind of equation, so you can try to use a Taylor expansion, and then use this differential equation to establish the relation between these coefficients. And this method, it's this series solution actually is quite general. Okay, and secondly, you need a fix by the boundary conditions. But if we don't have boundary conditions, actually, you can have this series to be any number, or you can have must have some eigenvalues to be discrete, right? And the thirdly, and this one can be apply that to, for example, to later on we're going to see that for the hydrogen atom, okay, a harmonic oscillator, many kind of problems, okay, and actually it's quite general for any PDE. For example, for the equation in the electromagnetism. So I don't know, have you already learned, for example, the solution of the electrostatic equations, the Laplacian in the three-dimensional space. So if you have learned that, you know that you probably also already know how to find out some other kinds of polynomials, such as the Legendre polynomials, Laguerre polynomials. Okay, and that's useful to find out the solutions of the electrostatic potential and the fields, in the three-dimensional cases. Okay, so on and so forth. Okay, right. So that's pretty much what we have for today. So let's see if we have some kind of questions.